Hello everyone! This video illustrates how the District Lab H Simulation Studio software can be used to analyze the robustness of a heating network. We will base this demonstration on a simulation scenario that represents the behavior of a 450 megawatt heating network during a cold winter month under the assumption of non-availability of a production site. As can be seen from this view, the study network is supplied by 5 main production sites: the Solvay site to the south, Villeneuve in the center, Biomax to the northwest, Île d'Amour to the northeast, and the Poterne site to the east, which is affected by the unavailability hypothesis. This map view shows 4 colored dots representing the zones of influence of each site and confirms the unavailability of Poterne. Let's use the curves to analyze the consequences of this scenario for some of the consumers affected. For example, substation 257T, with an initial graph tracing the evolution of the control valve position at this consumer. Over certain time periods, we can see that the position of the valve is 100% saturated. This means that the energy demanded by this consumer is not fully transmitted by the network. This is due to a drop in the differential pressure across this consumer, which reaches values of around 0.5 bars, causing the critical temperature to rise to very high levels. Remember that the critical temperature is the minimum temperature that the network must reach to satisfy the consumer's demand. In addition to highlighting these phenomena, District Lab H Simulation Studio can also be used to analyze the consequences of a shortfall in energy delivered to the consumer. The fourth graph from the top shows the difference between the secondary flow set point temperature and the temperature actually reached, with a difference of just a few degrees. The drop in differential pressure can be explained by saturation of the pumping units at the Villeneuve power plant, which can be seen very clearly on this hydraulic characteristic graph, showing the evolution of the hydraulic head gain as a function of the volumetric flow rate. Saturation of the pumping units is not visible at the other production sites. These phenomena are linked to the characteristics and intrinsic positioning of the various production points on this network. The first tab of curves gives an overview of what's happening on this network from a production point of view. The graphs in this tab show a significant discrepancy between the total power demand in violet and the power actually delivered, with a difference of around 30 megawatt between 300 and 330 megawatt on January 17th. The graphs show a fairly clear saturation effect on the flow temperature, visible in the second graph from the top, mainly on the Villeneuve site, which is responsible for load following and therefore sees a flow that is too high in relation to its own production capacities. It's interesting to switch to the map view for a global view, with a graphical theme representing the temperature field at pipe level and a binary black-white color scale to represent consumers. For a regulating valve position above 90%, that is close to saturation, the consumer is colored white, indicating a very high risk of unsatisfied demand. By positioning ourselves in time on the morning of January 17th, which is the moment of the most demanding scenario for the network, we can observe the distribution of all consumers who are affected by the unavailability of the Poterne production site. The consumers affected are located close to Poterne, but quite far from the Villeneuve power plant, which is unable to deliver the required temperature. This video illustrates how the District Lab H Simulation Studio software can be used to study cases considered extremely interesting by operator companies who need to anticipate and analyze the consequences of a production fault. This work was carried out in an energy context characterized by gas supply tensions. Thank you for your attention.